Yeah, I just want to add real quick. All of our cables will support 6-wire. So even if the sensor is not a 6-wire or sense-enabled sensor, the cable will allow your instrumentation to actually read what that voltage drop is. And again, this all goes back to the fact that load cells are ratiometric, right? So that cal data is a function of 10-volt excitation or whatever the voltage is on that cal cert. And oftentimes customers don't realize that it's not quite getting what they think is getting to the sensor. So 6-wire, if your instrumentation supports it, always a good choice, whether it's just in the cable or as we do on many of our calibration grade sensors, we'll actually take the sense all the way to the bridge level. So through the connector and to the solder pads for the bridge. So ensuring maximum accuracy there.
Mhm.
All right, Jacob, back to you.
Thanks. So now we're going to talk about strain gauges a little bit. So there's different styles of strain gauges, but they're all doing the same thing, right? They're all measuring strain along a certain direction. So you see there's, linear, shear, Poisson, and chevron gauges. And ultimately, so long as the grid lines are matched up to your strains, you're going to be in good shape. And we'll talk about grid lines here in the next slide. So here's a strain gauge up close. And the grid lines are those thin lines that are going across the gauge. End loops are the thicker sections at the end of the grid lines. The solder pads are what you make your connections with. The fiducials, those can look different for different types of gauges, but they help you align your strain gauge, which is very, very important. The backing, that's what your foil is bonded to, and that's also what you're going to use to bond to your spring or your flexure. And number 6 is going to be an optional encapsulation. That basically just protects your grid lines. Yeah. Next slide.
Jacob, when would we do the encapsulation? When would that be a good choice?
Yeah, so it kind of depends. Most of our gauges we don't use the encapsulation. We'll put a conformal coating over top of it. There's some applications where maybe it's like where outgassing is a concern, where some of the conformal coatings you would want to put have some outgassing issues. So the encapsulation's an easy way to kind of avoid that issue. Alrighty, and so gauges can be compensated for a variety of different issues. Self-temperature compensation. This is when the strain gauge can be compensated to kind of match its thermal expansion to the spring. So you can think about if you use the same strain gauge on an aluminum spring and a steel spring, those springs are going to expand and contract differently with temperature. And you want to match your strain gauge to it. And that avoids some, apparent strain that isn't correlated to a force. And then on the right there, modulus compensation. If you remember back to mechanics of materials, the strength of a different material, the modulus of elasticity, that can change a little bit due to temperature. So if you're measuring force, in the outside in the winter and it's 40 degrees, and you're on that same test in the summer when it's, here in Phoenix gets pretty warm, the material properties of your spring change, and that can affect your output because you have a weaker spring. The gauge can be compensated for that. It can basically change its gauge factor so that it offsets any loss or gain of strength of the material. Next slide, please. So there's two main types of foil gauges. There's plenty more, but these are the two main ones. We'll start with Constantin. It's a copper nickel alloy, and that makes it very easy to solder to. It's a little bit less thermally sensitive. It warms up quicker. It's a very common material, but there are some drawbacks. It has a lower gauge factor, and it's not as easy to heat treat, especially to the extent that you would need to, in order to have self-modulus compensation. So if you want to modulus compensate a constant bridge, you have to add modulus trim. So basically, special resistance on your excitations that change their resistance to basically lower the voltage applied to the bridge. And constant gauges are best suited for room temperature applications. They're definitely not good for high temperature applications. And we switch over to Karma. That's what Interface uses. It's a nickel chromium alloy, and it's able to be heat treated in a way that makes it way more conducive to self-modulus compensation. So it doesn't need extra trim in order to modulus compensate, because that'll reduce your output. And in addition to that, it also has a higher gauge factor, which means better resolution, better performing load cell. It's a harder foil, so it makes it a little bit harder to roll, but it does lead to a little bit better performance, and definitely is more reliable at high temperatures. It's not as common of a material, so it's a little bit harder to source for some companies. But Interface has been using this, I think, since the beginning, right? 56 years. So it's pretty much our standard. So all these drawbacks really don't bother us all that much. And in the top right, you'll see the gauge factor formula. So this is, a property of the foil, and it's basically what correlates the change in resistance for a given strain. So a higher gauge factor for the same strain means you're getting more output for the same amount of deflection or strains. And that's really important for fatigue life, which is why we use Karma. Next slide, please. So how is a gauge made? It's very similar to the process that's used to make what we're all using right now, right? Computers. It's photolithography. So the foil is going to be bonded to the backing, and then there's going to be a photoresist applied over top, and using a mask and a UV light source, the photoresist can be hardened in certain locations that then reveal the foil that we're going to etch away. And once all that's done, you're left with your gauge. Next slide, please.
Jacob, that's the process Interface uses to manufacture our proprietary gauges, correct?
Yes, yes.
All right.
And all right, so switching over to putting the gauge on the flexure or the spring. You're going to want to make sure that your grid lines are aligned with your strains that you're trying to measure, that you're trying to correlate to the force. So grid lines not aligned with the strain will be less sensitive to that loading mode. So that can cause nonlinearity and other performance issues, but it also is how multi-axis load cells work, where some gauges or the bridge that's wired with those gauges are more sensitive to certain loading modes than others, and that's how you get a multi-axis cell. And then I think we have an animation coming up here. Could you click to the next? There we go. So you can see the grid lines there are aligned with the principal strains, and that's from a simulation. Might be kind of hard to see on your computer screen, but those are little arrows kind of pointing in the way that the material is deforming. And you want your strain gauge to be in a uniform strain field. And that's really important because that can cause nonlinearity issues. And it's also something you want to take into account because assembly is never going to be perfect every time, right? So you want to make sure that a gauge that's a little bit high, a little bit low, a little bit to left or right isn't going to throw off the performance of your load cell. Next slide, please. So kind of going back to the tension and compression that we talked about earlier, you can see in the photo on the bottom left that the grid lines on the right are directly aligned with the strains, while the grid lines on the left are 90 degrees to that. And so the one on the left is going to be the compression gauge. And you can kind of think about how it's going to stretch the grid lines kind of hamburger style, right? While the one on the right is going to stretch it long ways, which is going to increase its resistance. Next slide, please.
Actually, Jacob, if I can touch on 2 points here, this is
Yeah,
a great,
totally.
this is a great view. So Two things. First, as he's highlighted, depending on where the gauges are and how they're placed, they're going to respond differently to the load. You only need 4 gauges, as we saw for a Wheatstone bridge, but interface on our low profile load cells will utilize 8 strain gauges per bridge. So we'll actually place the gauges in a manner that if there is by any chance a side load introduced, a bending moment, the various legs will self-cancel. So it will not manifest as a change in axial force measurement. So not only is the low profile design radially symmetric, which lends itself well for handling any non-axial load. We use 8 strain gauges, and then we do another step further called moment compensation, which we'll touch on. But I just want to highlight that. So through the design of the flexure, through the placement of the gauges and the types of gauges used, we can make these sensors very robust to reject anything other than measuring the actual axial force that's popping up. The second thing I want to highlight here is if you go through some of our products, you're going to see that, as you saw earlier, our standard 1200 series has the female threaded hole in the top, right? Well, if you look at this, you can see how the force applied at the end of that top section, which would be threaded, transfers all the way through the center portion out to the outer beams where the gauges are. So our 1200 or 1100 or 1000 series will have a female threaded hole. We talked about the importance of mechanical mounting and the thread engagement and making sure you've got good tight connections and potentially even preloading. That is because it lends itself for much better consistency of how that load propagates through to the bridge. So if you look at our calibration grade sensors, for example, our 1600s, they have a pre-installed cal adapter. So that center stud that we see here in this picture would be threaded in, it would be locked at the factory, and it would be preloaded to ensure that as you operate within the capacity, you're not going to get any change in how those threads interact with the center hub to ensure that you don't get sudden shifting of which threads are loaded, where the load goes through, which can then dictate a very slight subtle change to the beams, right? Now our 1800 series takes it one step further and is what is depicted here, and it's a feature we call an integrated stud, where it's all part of the same machined element. And we do this for some of our more demanding applications, some customers that really want the best performance. We'll do an integral stud. So it's all one machined element, and it completely eliminates the chance of any variability there in terms of how that force is introduced much further away from the gauges and then propagates down through consistently every time to where the bridge is. So
That's a good point too to bring up the 1800 series, because not only do they get the integral stud, they also get double gauges, and you can see that the nonlinearity of one gauge being misaligned one way or the other is somewhat random, right? So by doubling the amount of gauges, it can help cancel out any nonlinearity issues.
That's 16 gauges, right, per bridge?
Yeah,
So
16
quite a bit.
bridge on 1800s. Yeah, yeah. Alrighty, thank you, Brian. Next slide, please. There we go. And so we talked about creep and creep compensation before, and how that's achieved is by changing the end loops. So the end loops, the longer the end loop, the more positive creep response of the gauge. And you can kind of think of that as the longer end loops, the bigger end loops kind of give more anchoring to the gauge. So they're kind of like responding more like the flexure is. And we can use the end loops to basically match. That's how we match the gauges to the load cell and that capacity. And then the backing is also pretty important when it comes to creep compensation as well. That's what's transferring all the strains from your flexure into your foil, which is changing its resistance and leading to your output. One other interesting aspect too is the distance from the foil edges or the end loops to the edge where the gauge is cut is pretty important. If it's too short, it can basically kind of act like a different end loop. So next slide, please. Why do we make our own strain gauges? I actually think this answers a question in the chat of are the modulus compensation done at in the load cell by interface or in the cable and signal conditioning? So that's a good question. Interface, we heat treat we make our own gauges, we heat treat our own foil, and we're able to thermally match the performance of the strain gauge to our materials. So we do that in-house. We qualify every lot of gauges for these characteristics. And that's pretty unique. So we match our gauges to our flexure material, and since our gauges are karma and we're able to modulus compensate them due to that heat treating process, they don't need the compensation resistors that even further reduce your output. Um, so we have higher output, better resolution than a lot of other load cell companies. Um, and one point we're going to touch on a little bit later too is this gives us opportunities to optimize the gauge and the flexure as one cohesive design, which we'll talk about in a little bit.